Hello, ladies and gentlemen. My name is Khatri. I'm a structural engineer in Las Vegas, Nevada. I work all over the United States and also in Canada and internationally. Thank you for attending today's session on report number 4, where we are continuing our series on looking at the Champlain collapse. I've done some more analysis to share with you. This is report number 4. There are 3 previous reports to this, and I'm pleased to present my results to you today. So these are some links to my previous reports. I've done 2 reports on the Champlain Tower Collapse, and I've also done a report a few years ago on concrete buildings, which I encourage you to take a look at. And this is for your information to see some of the background that I've done on this topic. So for clarification, I just want to be clear. I've said this on the other 3 reports. I'm just going to repeat it very briefly. I am Dr. Khatri. I'm not representing any organization or government agency. I haven't been hired by anybody to look at this project. I did go to the site. I did visit the field. I did look at the plans. I've looked at a lot of documentation, but I'm not a hired expert by anybody. I'm providing this for information only. This is my 4th report on the Champlain collapse, and this is strictly for information only, for education. I'm not making any allegations or assertions or claims. I'm only sharing from my forensic experience, having been in this industry for 39 years and also was a faculty member, and I want to share information with the technical community and with the public to shed light on some important facets that I think are relevant to other buildings that exist today worldwide. So report number 4, we start with a technical analysis. The comments here, notes number 2, 3, 4, and 5 were discussed in the prior 3 reports. Today we're going to focus on the first objective listed here, which is I've done a structural analysis model to determine the effect of soil settlement on the upper frame moments, shears, deflections, and stability. And this is something that is not done under any building code. There's no building code or design practice in the industry today that requires structural engineers or geotechnical engineers to account for ground settlement in the performance of a building. And so I did this analysis mainly out of curiosity and also to follow up on a hunch that I had about 2 months ago after visiting the site, that what would happen to the building if a column were to sink. And so I did a very simplified model. I'll show it to you and share the results with you. That's the purpose of today's presentation. And so report number 3, we discussed the effect of corrosion on steel and concrete. We discussed what could happen to the footing with a concrete pile cap. We discussed the column slab connection. Today we're going to look at what happens to the shears and moments from the rotation of a foundation settlement and the effect of settlement itself, the vertical movement of a particular column. How does it affect the rest of the building? The results from today's analysis, it's a very simplified analysis. It's just a single frame, one story, but it has application to buildings worldwide, because the principle of the analysis shows, and you'll see it in a moment, what happens when a building settles and how does it affect the structural performance of the rest of the building. We start by looking at a very simple model of a single portal frame. This is a simple moment frame system. We all studied this in college many times in our undergraduate program. And what we're going to do with this portal frame is do a very simple analysis where we will try to destabilize the frame by allowing one joint to slip. So in the top of the diagram you see case A, which is a traditional fixed base model. In this particular case I have modeled exactly the loads that I calculated from the Champlain building for a typical tributary frame with the dimensions that I got from the plans. You have a dead load and live load on the top part of the frame for the level 1, and then you have axial loads upwards of 600,000 pounds coming from the 13 floors up above. And you have joint A and joint D are fixed base. You see that in case A with a rigid frame. And that's a traditional analysis. That is what structural engineers do on designing buildings like this. We do the case A analysis and we design the building based upon that. We assume throughout the life of the structure that joints A and D will never move, that they will remain stable. And that obviously is not happening, not just on this building, but is not happening throughout. As a forensic engineer, I can tell you that the joints are moving. Case B, which is the frame below, we are now adding a stiffness model for the soil on joint number D. And what I've drawn in there for you is a roller connection for the horizontal displacement. I'm not modeling horizontal movement at this time. That would just get a little too complicated. So it's a simplified model. The vertical stiffness is the K soil, and then there's a rotational spring stiffness, KT, which is the torsional stiffness. And I'll explain those in a moment. Vertical stiffness is modeled using a linear elastic stiffness model. In this graph, I've shown schematically how that stiffness really looks. On the vertical axis, you have the vertical compression force on the column acting downward on the footing. Everything here is positive, but obviously in the actual model, it would be a negative deflection. The delta Y on the horizontal axis is the vertical deflection, and the dashed line represents the actual nonlinear soil stiffness model, which most soils are very nonlinear. And we're approximating that using an ideal linear elastic curve because hopefully we never reach the nonlinear behavior. So most of our deflection will be occurring on the very far left of the diagram where the linear elastic stiffness modulus is applicable. That number would come from a soils engineer. In the structural model, we assume that K soil is infinity. We assume it's perfectly elastically rigid, which I am now removing that assumption and putting in some linear elastic model, and I'm varying that linear elastic K modulus and degrading it. In other words, I'm starting from a very high number and then I'm reducing it until we get deflection. And then I'm seeing what happens in the structure, what happens to the moments. And again, I want to reemphasize, this analysis is not done on any building that's done for design, not only in California, but anywhere in the United States, or for that matter in the world. There's no code that requires this. So this is somewhat of an interesting analysis in the sense that it's not really looked at. And I don't think, again, I will be a little bold here to say, I don't think that there's any real research papers that have been written on this, but of course I could be wrong. There's a lot of research going on out there that I'm not aware of, but nothing that I've personally read or seen recently anyway. And the rotational stiffness, which is the coil spring, same idea. The actual soil is highly nonlinear, and here we have on the vertical axis the moment rotation relationship, the rotational moment in kip inches versus the rotation of the foundation measured in radians. No specific numbers here because I'm only doing this analysis really to see just varying the numbers from infinity and degrading the rotational stiffness down to the point where we get some rotation, we get some deflection to see the effect of rotational stiffness degradation on the frame. What happens when joint D loses its fixity and that joint is allowed to rotate? How does that affect the other column joints? That's the purpose of today's analysis. This is case A, which is the standard case. Fixed base model. This is done all the time. The program we're using here is RISA 3D. It's a two-dimensional model. And you can see everything is nicely symmetrically distributed. You can see the loads are 50% shared between the two base joints. The moment diagram is very symmetrical. But pay attention to the numbers here. I want you to look at the left corner where you see the moment of 44.5 foot kips. Pay attention to that and pay attention to the moment on the right, which is symmetrical, and see what happens as we start to move the lower right joint number D, letter D, downward. In this analysis, I have reduced the stiffness in joint D, which is the lower right joint, and you see the deflections there. We're getting about 1.25 inches of deflection in node number 4, which is joint D on my diagram. And see what's happening to the moment diagram. The moment diagram has gone asymmetrical. The moment on the far left is now 58.1, whereas before it was 45, so it's increased substantially. The moment on the right joint has dropped from 48 to 31. And what this is telling us, which I did sort of predict this, I'm just going to say, that it makes physical sense that when one leg starts to weaken, the other leg takes more load. And so that fits with, human expectation. If you are walking with two legs and your one leg is hurt, your other leg is going to pick up the load. It's simple physics. The building will redistribute the axial loads and redistribute the stresses to the stronger remaining leg. Makes sense, and that's exactly what's happening here. The problem that you have with this is that that joint on the far left is not designed for those higher moments. It was designed for a static equilibrium condition that was symmetrical. And this is where the problem occurs, because when you have the redistribution of the stress, the new loads are higher than what was there before, and now that deflection in that column is now affecting the rest of the building, which will lead to instability. And we are getting horizontal deflections, as you can see. Look at the X dimension there. We're getting horizontal drift that's occurring in the frame. So the frame is drifting to the right, which will lead to a P delta effect. Now in this case, it may be okay with only 1.25 inch deflection, but it can easily get out of hand. You'll see in the next slide. This is the same case, case B. Here we have the same deflections. I've printed for you another slide down at the bottom which shows the moment distribution, the moment redistribution, I should say. And again, you're getting asymmetry. You can see the moment diagram on the far left column has shifted dramatically, and the loads have gone up, which puts extra strain on that beam column connection, and also it affects the shear diagram as well. In this slide, I have released the rotational stiffness, so now we're getting rotation at the joint D. I've softened the rotational spring, and you can see the deflection on the lower right, which is node number 4, or joint D, is up to 6 inches. And this has affected the stress distribution as well. You can see that it's very asymmetrical. This is the shear diagram. You can see the shears are no longer symmetrical, and the same thing is happening with the moments. Between the two, the vertical deflection has a more dramatic impact on the moments and the stresses than the rotational stiffness, but they're both bad, and they both lead to unstable structure. This is a schematic diagram of the pile cap rotation, where we have the column coming in, there's a pile cap, and I've schematically shown here what happens when you have cap rotation, what happens when you have vertical deflection. These are the components that can and should be measured in a building. If we are having this issue occurring in any building, it will demonstrate itself somewhere on a diagram like this, which can be measured. And so measurements to see if the building is deflecting are highly valuable, because that will tell us whether or not the building is sinking, if it's sinking by how much, and that will give us a prediction of what the stress increases is in the columns. Even though the analysis that I've done is a single portal frame, it's a simple frame, it applies to a multi-story structure just as well. It probably will show worse in a multi-story structure because you have multiple levels. But the principle, the structural principle that I'm driving home today is that deflections matter. They matter a lot. And they're not in the code, and they're not considered in design, and they're not part of our general practice of engineering. They're not within the normal bandwidth, if you will, of what's defined as generally accepted professional practice. Definitely not. Maybe it should be, but that's a new discussion that will have to be looked at on the coming horizon. In this simplified analysis, we can conclude that foundation settlement will affect the column, slab, and beam moments. That's clearly obvious. It will affect the P delta due to the lateral translation. At some point, there will be extra P delta moments introduced to those columns. Vertical settlement downward increases the moments in the upper moment joints, for sure. And it will lead, at some point, to structural instability and eventual collapse. How much depends on the building, depends on the type. There are no rules of thumb here. This is new territory that we're in. We're looking at something that really hasn't been examined before, and it requires some attention. And the best that we can do as structural engineers in working for our clients is to do this analysis on a case-by-case basis and do very accurate measurements of the building to see if the building is moving. If the building is moving, then the next question is by how much? And then we can see whether or not it's detrimental or can it be ignored. The conclusions presented today apply to a multi-story model. A multi-story model would look something like this, where you would have a variable stiffness foundation, basically an elastic foundation, except an elastic foundation has a continuous modulus at the base. In this case, we would be degrading certain springs and leaving other springs rigid, or in other words, allowing for variable deflection. And that's where things start to get really complicated, because which column is moving, how much is it moving, is the building sinking in one direction, is it sinking towards the center? That's the part that we don't know. That's the part that we have to measure. But it definitely impacts all of the joints, all of the frames. It impacts the stresses in the building. And it does cause problems, and it is a structural concern. Whether or not this is a root cause of what happened in Champlain remains to be seen. We have to wait and see with more data and see what the official investigation reveals. But based on what I've done here today, I think we can definitely shed light on something here that needs immediate attention on all of the other buildings that are similar to Champlain that require some form of structural investigation. I've included this slide, which was in my third report, just as a recap to explain how the pile foundation system works. In the case of Champlain, it was built using skin friction piles, where the friction between the piles and the soil is the governing load path. And if that skin friction slips, then you have problems. We have a terrible example of this occurring in San Francisco right now with the Millennium Tower that is sinking and tilting. And it's exactly the same situation as this diagram, except that in that case, in my diagram here, the piles went into bedrock. In the Millennium Tower, the piles did not go to bedrock. And that is probably a much more complicated situation, but the principle is the same, that as the building continues to sink, it has a dramatic impact. It has a detrimental impact on the structure above. And so if we were to have just even modest deflections, it will cause column rotation at the garage level. It will cause distortion of the column on the first floor. It will aggravate P delta moments, which potentially lead to buckling and instability failure, and it will be weakening the upper story columns. Now, that mathematical equation of how much deflection and how it relates to the upper story columns gets rather detailed, and I am looking at that right now. I will produce some analysis on that and share that with you in the coming weeks. But this is a consideration that is not considered in conventional design and is potentially a very potentially strong root cause failure that could have happened. I'm not saying it did happen. I'm not saying it's definite because I don't have enough information. But I've done enough work in this industry on different types of tall structures that I can certainly consider this to be a potential contributing cause of collapse. And it's something that we need to look at as engineers that are working in this industry. We do need to look at this on other existing buildings, because this is a point of failure that can be measured. This is a root cause that can be measured in the field, and we can document it, and we can potentially predict a collapse before it occurs. Because if a building is sinking non-uniformly and the caps are rotating, we can measure that using instrumentation, and then we can tell our clients whether or not their building is shifting. And so here I propose a system that we are currently using in my firm for clients to evaluate their existing buildings, and that is a system of structural monitoring to check the floor slab deflections. And I've shown a schematic diagram here which shows a high-rise building sitting on a subterranean parking structure, and we will, meaning my firm, will survey the slabs to see whether or not they are moving. We will do a full-scale survey and measure the relative deflections of that subterranean parking structure to see if it's shifting, to see if slabs are settling, and to see if they are level or are they rotating. And then part two is we will check the column alignments. The column alignments are very important. Obviously, if a column is not vertical or column is distorting, that's a cause for concern. Now, it could be that those columns were not aligned to begin with. No building is built perfectly straight and square. I understand that, and we have to accept that. But there are tolerance requirements. There are tolerances that we can check it against. And this is the area where I think we as structural engineers should be looking at this when we're called in to look at a building. How do we know whether or not that building is potentially in a collapse mode, may have already started to collapse and we haven't noticed it? This is an analytical procedure that we can do in the field to measure and see whether or not that building is moving. And I highly advise that we do this as part of our scope. For report number 4, my conclusions, which follow through with reports number 2 and 3, foundation and footing settlement is a potential cause of failure. We do not know for Champlain without any measured data. Structural monitoring is essential. We've got to monitor our buildings. We've got to look at the column alignment. We've got to look at slab deflections. This is very important to keep track of our structures like in this category, so that we can at least take either precautionary or mitigation moves, or at least issue a warning to an occupant or occupants that this building is dangerous. Again, I thank you all for listening to my talk today. I very much do appreciate your comments, your thoughts, and the likes on the video. And I wish you all guys well. I've given you my email address if you want to contact me, and I thank you again for attending today's presentation.